Okay, you guys, let's recap the lesson. So today what we talked about in rational functions were things called discontinuities. So if a graph stops or has to go in a weird way towards infinity, that is going to be discontinuous. So these rational functions have weird things to them because you can't divide by zero. So for example, watch my finger. Here's this graph. I go along, I'm continuous. So I say, watch your finger. If you have to pick your finger up, it's discontinuous because we got an asymptote. They go along, and then all of a sudden right here, there's a hole, and we're going to talk about the hole, and you fall through it. It's discontinuous there. So this particular graph is discontinuous at the asymptote at x equals 3, and there's a hole that it falls through at -2. Okay, so let's talk more about discontinuous. Okay, here's the graph I gave us. Okay, oops, I got a little mistake. Let me fix my little bluebie here. Here's my function, and if I graph this, you'd think it's some kind of weird graph, right? Some kind of curvy whatever. Actually, no, I wanted to start, and then when I graph this graph, and I do my f of x, my y equals, wow, all sorts of crazy stuff on this graph, okay? Parentheses, x plus 2 divided by parentheses, I got an x squared minus x minus 6, and if I graph this, well, let me get the right window. All right, we'll fix the window so it works better. We'll go from -10 to 10. We'll go from -10 to 10. Now we'll graph it. Take a look at it. Okay, there we go. It looks like this. Well, that asymptote makes sense to me. So if we were to factor the denominator, we know the multiples of 6, -6 are -3 and -2. Together they make the invisible -1 for the x term, so it is factored. And then we take a look at these two relationships. We got an x plus 2 over an x plus 2. Well, first of all, we cannot divide by 0. So we know for sure that x cannot equal -2, because if it's -2, -2 plus 2 is 0. Cannot do that. You divide by 0. And then here, if x were 3, right, we'd have 3 minus 3 is 0. So sure enough, even our graph shows it, that we cannot have. You see the asymptote there? And we know there cannot be a value at 3, so there's an asymptote, okay? Now this hole's weird, because if I were to use my trace button, if I go to trace, and if I go to -2, then you see there's no y value, because there's a hole there. Technically, this -2 does not exist, because it can't. But for some reason, there's a hole, not an asymptote. So we talk about this. Since we can cancel out the x plus 2. So if it's removable, if the problem's removable, it's a hole, okay? So we talked about this. If the problem being divided by 0, is removable, we end up with a hole. So it's removable, we get a hole. But if it's not removable, see the x minus 3, there's no way, that does not cancel out. It's stuck. You're stuck with x minus 3, which means you're stuck with the discontinuity of 3, so we get a vertical asymptote. So if it's removable, if the problem's removable, it's a hole. If you can't get rid of the problem, it's an asymptote, okay? So then, okay, then we looked at this a different way, okay? We did it so that the x was on top. I completely re-graphed this one. Clear, and let's do it all over again over here. No, we don't want that. Clear. And we'll do the same equation, which is a little bit different. And I'll do an x squared minus an x minus a 6 divided by x plus 2. And if I graph this one, that's surprising. I wouldn't have thought that would be a straight line at all. But let's see what happens. If you factor again x minus 3, x plus 2, then what happens is the x plus 2's cancel, and all you're left with is this, y equals x minus 3. Well, we can graph that, start at -3, up 1 over 1. But there's got to be a discontinuity at -2. So right here at -2, let's check it out. If x, we know x cannot equal -2, even though it cancels out, the original function has it. Okay? So it cancels out, you get x minus 3, but let's check out what's going on at, if I go trace, and I go to -2, and again, there's a hole. There's no value for y at all. So that tells me that at the value of x equals 2, so there's a hole, So a hole right here at -2. Let's see, 1, 2, 3, 4, 5, -5. There's a hole, okay? All right, so that's kind of what we talked about. For homework, what I did is I gave them the cutouts, and the cutouts were in the book from page 409 to 417. We cut out the graph, we matched it to its equation, okay? And that's what's going to be due for tomorrow, okay? That's all I have. If you have any questions, come see me. The cutouts were from page 409 to 417.